EGR 6083, Quality Control and Improvement, Module 1, Lecture 1, Introduction to Quality Control. The learning objectives for Lecture 1 are to discuss the different dimensions of quality, discuss the evolution of modern quality improvement methods, discuss the role that variability and statistical methods play in controlling and improving quality. The reading assignment is Chapter 1, pages 3 to 46. First of all, what is quality? You see this term everywhere on everything that's manufactured, from hotels to food to cars. Everything has this quality sticker on it. So there's a lot of different definitions of quality. Our textbook lists 8 dimensions of quality. Performance. Will the product do the intended job? Reliability. How often does the product fail? Durability. How long does the product last? Serviceability. How easy is it to repair the product? Aesthetics. What does the product look like? Features. What does the product do? Perceived quality. What's the reputation of the company or its product? So oftentimes this one is, we tend to associate certain companies with high quality products. Conformance to standards. Is the product made exactly as the designer intended it to be made? We can add additional dimensions of quality for service industries such as banks. 1. Responsiveness. How long did it take for the service provider to reply to your request for service? Professionalism. Does the service provider have the sufficient knowledge and skills? 3. Attentiveness. Does the service provider give the customer caring and personalized attention? So the traditional definitions of quality, there are many. If you look in the dictionary, there's many terms for this, but oftentimes you tend to see these 3. Quality is, first one is quality is what the customer says it is. Quality is fitness for use. Or quality is conformance to standards. So all 3 of these are sort of your traditional ways of looking at quality. The modern definition of quality, and the one that we're going to use for this particular class and the one that's used for quality control and improvement, is the following. Quality is inversely proportional to variability. So the example the book uses, there are many examples of this, but this was an example that a U.S. automotive manufacturer in the 70s did a study of the warranty costs for transmissions in the United States manufactured transmissions compared to Japanese manufactured transmissions. What they found was that the companies in the United States were spending many times more money on warranty issues for their transmissions compared to the Japanese. What was causing this? Why were the United States companies like Ford and Chevrolet, General Motors, spending all this money on warranty costs? Why were their transmissions failing at a significantly higher rate than the Japanese were? When they got to looking at the actual data, what they found was that the Japanese transmissions had a much narrower number of variability in their manufacturing. So even if a product, so what this graph shows the that even the United States products were all manufactured within specs, but there was much more variability. So, for example, LSL is the lower limit spec. USL is the upper limit specifications. So if you notice, all the transmissions made in the United States were manufactured within spec. However, the Japanese transmissions were manufactured to a much narrow tolerance, and so that much narrower tolerance led to less variability, which meant that their manufacturing processes were much more precise and efficient. And part of the problem here is that, when you manufacture something as complicated as a transmission, there are literally hundreds of individual parts inside the transmission. So, if each one has a little bit of variability, if you multiply all those variabilities together, you end up with a product that has much more variability than if than the Japanese transmission. So quality improvement is the reduction of variability in processes and products. The transmission example illustrates the utility of this particular definition. An equivalent definition that is useful in service or transactional businesses is that quality improvement is the elimination of waste. There's some terminology that we need to become acquainted with when we talk about quality control. First of all, every product possesses several elements that jointly describe what the user or consumer thinks of as quality. These parameters are often called quality characteristics. Sometimes these are called critical quality characteristics. Some examples are physical, length, weight, voltage, viscosity, etc. You can also have what's known as sensory, taste, appearance, color. And then there's things that have to do with time, like reliability, durability, serviceability. Quality characteristics are often evaluated relative to specifications. We can have what's known as the target or nominal values. These are the desired values. For example, if you're manufacturing a boat, you may have a certain length of the boat, a certain weight of the boat, and you have a specified weight and length of that particular product. You often have what's known as a lower specification limit. This is the smallest allowable value, or an upper specification limit. This is the largest allowable value. Products that fail to meet one or more of their specifications are called non-conforming products. A specific type of failure is often called a non-conformity. A non-conforming product is not necessarily unfit for use. However, a non-conforming product is considered defective if it has one or more defects that are serious enough to significantly affect the safe or effective use of the product. When we manufacture products, we have to use statistical methods to determine if the product is being manufactured to certain specifications. So here we have a process that's making some product. We input the raw materials, the components, information, whatever you need is fed into the process. The process often has what's known as controllable inputs. So these are things we can affect. These are maybe machine specifications. There are also some uncontrollable inputs. These may be things like materials that we're getting from some other manufacturer, or it may be some product that we're like aluminum we're digging out of the ground, for example. We can't really control how much impurities are in certain base kind of products like aluminum, iron, that sort of thing. Those are uncontrollable inputs. The controllable inputs are inputs that we can physically control inside the plant where the product is being manufactured. So part of the process is measurement, evaluation, monitoring, and control. So what we're going to do is we're going to measure the output to some quality characteristic, for example, like the length of the product we're manufacturing. We're going to evaluate if it's being manufactured within tolerance, and then we're going to take control and adjust our process to improve our quality characteristic. One of the most useful statistical methods we will use in this class, we will see introduced later in later chapters, is what's known as the control chart. The control chart makes use of the fact that we take samples from a manufactured process, and CL is the control limit. This is, for example, if we're trying to manufacture a bolt for a certain length, the control limit is what the target goal is. This is what we would like to produce. Well, of course, any manufacturing process is going to have variability. Not every product coming off an assembly line is going to have exactly the same specifications. There's going to be some deviations just due to normal variability. But what we can determine, we can set what's known as a lower control limit and an upper control limit by statistics, and we will learn how to do this in future chapters. So as our product is being manufactured, we take samples from the manufacturing process and measure them precisely and plot them on the control chart. So this, on the bottom, it acts as this time. So this product was taken, sample was taken before this product, sample before this sample, etc. So as the process is being manufactured, maybe we take 10 samples in one 6 hour period, we wait 6 hours, we take another 10 samples, and we plot these. We measure the specification we want to control, and we plot this on what's known as a control chart. Now, hopefully, we hope that all the samples fall within the upper control limit and the lower control limit, and oscillate around the control limit. If they don't, then our process is not in control, and we have a problem. So we can go back and we can see if there was a particular operator that was causing the problem, or maybe something shifted in the process. Maybe our machine is out of tolerance, and maybe it needs adjusting. So we'll learn a lot about how to use control charts in future chapters, but I wanted to put it in here to talk about specifically about one of our primary tools we're going to use to monitor quality control. So there are three different types of statistical methods in your normal quality control. The first is what's known as SPC, statistical process control. This uses control charts and other problem tools like histograms and cause and effect diagrams, etc., that we'll learn how to use extensively. These are very useful for monitoring processes and reducing variability through elimination of what's known as assignable causes. The other method is what's known as designed experiments. These are discovering the key factors that influence the process performance. So basically what we can do is we can vary the controllable input factors, adjust them, and try to see what the effect it has on the output product parameters. So maybe, if we're manufacturing a process and it has to have a certain temperature, maybe we adjust the temperature slightly up and down, and then we see what the effect is on the output of our process. The last one is what's known as acceptance sampling. This is where we inspect and test products. We take samples off the assembly line, and we inspect them and we test them. The book goes over a fairly extensive historical development of quality control, and it's definitely worth reading. Here I'm going to point out 3 or 4 of the really key figures of this quality control procedure. The first one is Walter Shewhart. Shewhart was trained in engineering and physics back in the late 20s. He had a long career at Bell Labs, and he was the first person to develop the control chart about 1924. Shewhart also came up with what's known as his guide to improvement. It's his act, plan, do, check. So first thing is plan a change or experiment aimed at a system improvement. Carry out the change. Often it's what's known as a pilot study. Check the results. What did you learn? Act. Adopt the change or abandon it. If adopted, make sure it leads to permanent improvement. Next person to come along that actually met Shewhart and learned a lot from Shewhart at Western Electric was Deming, W. Edward Deming. Deming taught engineering and physics in the 1920s and finished his PhD in 1928. He had a long career in statistics, working for the government. During World War II, he worked with the U.S. defense contractors, deploying statistical methods to improve production. He was sent to Japan after World War II to work on their census, and held a series of significant lectures with the Japanese manufacturers, and they adopted many aspects of his management philosophy. And this, a lot of people think this is, along with their hard work ethic, is one reason that Japan was able to really improve their manufacturing capability after World War II and begin manufacturing products, automobiles specifically, with a significant performance enhancement over the classical methods that General Motors and Ford were using back in the 70s and early 80s. Deming stressed basically that quality is a continual, never-ending improvement. Deming came up with what's known as his 7 deadly diseases of management, and one is the lack of consistency of purpose. What's the purpose of management? What are we trying to do? The second one is emphasis on short-term profits. So here, it's great to have profits. It's great to have short-term profits, but if that's all you're focused on, and you don't develop the technologies and for the future, uh, that's very short-lived. I mean, there's a lot of companies that were around back in the early 1900s that are no longer around today. They were very profitable companies, but they did not spend a lot of money focusing on the future. A good example that actually a company that actually does a good job in this is Apple Computer. Apple spends a lot of money on research and development, and a lot of the stuff that they spend never comes to fruition. But a lot of key things do. For example, like the iPhone. Uh, that was a research project that started inside of Apple and went on for several years before they actually started making the actual phones. The next one is evaluation of performance, merit ratings, and annual views of performance. So this goes back. This actually can create heartache for the people that work for you. If you have this merit rating system and these annual reviews of performance, it can oftentimes lead to hard feelings and etc. And so if you don't treat your people right, and you know that has a huge impact on the how well the company's going to do. The fourth one is mobility of top management. Deming said that a lot of top management were kind of bouncing around between companies and shifting jobs and which leads to instability. They were never in a position long enough to actually do anything good. They were always worried about their next job, their next advancement. 5 is running a company on visible figures alone. 6 is excessive medical costs, and that's even more true today. Excessive medical costs are driving a lot of companies into the red. In fact, they're bankrupting a lot of companies, having to carry medical costs because the medical costs have skyrocketed. Basically, is the problem. The 7th one is excessive legal damage awards, and we've seen some of that in liability. That companies basically get sued out of existence due to poor management. Joseph M. Duran was born in Romania and immigrated to the United States. He worked at Western Electric, influenced by Walter Shewhart. You got to get a picture here that Western Electric and Bell Labs were the key drivers of this quality control, and you'd be exactly right. All these guys came from either Bell Labs or Western Electric. Duran emphasized a more strategic and planning-oriented approach to quality than Deming did. In fact, he formed what's known as the Duran Institute, that's still active organization, promotes the Duran philosophy and quality improvement practices. Duran came up with what's known as his trilogy: planning, identify customers and determine their needs; control, determine what you need to measure and set a goal for your performance; improvement, fix what's broken, be proactive, continue to improve a process that isn't broken. Improvement through innovation or technological advancement will often pay big dividends. The next leader in the quality control movement we want to take a look at is Philip Crosby. Philip was born in 1926 and was an author and businessman who contributed greatly to the management theory and quality management practices. Crosby's principle of doing it right the first time was his answer to the quality crisis. He defined quality as full and perfect conformance to the customer's requirements. As a quality control manager of the Pershing Missile Program, Crosby was credited with a 25% reduction in the overall rejection rate and a 30% reduction in scrap cost. So Mr. Crosby was really a key practitioner of the methods of Denning and Duran. In one of Crosby's books, he talks about 5 erroneous assumptions that people often make about quality. The first erroneous assumption is that quality means goodness or luxury or shininess. This tends to make quality a relative term that you can't measure. Only when quality is defined in terms of customer requirements can quality be manageable. The second incorrect assumption about quality is that quality is intangible and therefore not measurable. If judged in terms of goodness, then quality would certainly be intangible. However, quality is measurable by the cost of doing things wrong. More precisely, quality costs involve the cost of failures, rework, scrap, inspection, prevention, and loss of customer goodwill. The third erroneous assumption is closely related to the first two, and it states that there exists an economics of quality. Here again, one errs in thinking that quality means building luxuries into a product or service. Rather, quality means that it is more economical to do things right the first time. The fourth erroneous assumption has to do with the fact that blaming workers for the cause of quality problems. Without the proper tools, equipment, and raw materials, workers cannot produce quality products or services. Management must ensure that the necessary items are available to allow workers to perform their jobs well. The final erroneous assumption that Crosby discusses is that quality originates in the quality department. According to Crosby, the quality department's responsibilities revolve around educating and assisting other departments in monitoring and improving quality. So in other words, everybody has to be involved with quality, from top level management all the way down to the new guy that just got hired. There's several quality management programs that have existed since the 1920s. Statistical quality control had its origins back in 1920 with Shewhart and Deming. It was hugely popular during World War II in the 1950s. In the 1940s, they developed what's known as operations research. These were research teams within organizations that had the primary goal of quality management. Another big quality management program led out of what's known as the FDA and EPA back in the 70s. Total quality management. This was a movement back in the 1980s. The methods were actually pretty good in total quality management. The problem was is that and I was this is when I first got involved with the Navy tried to institute some of this total quality management. The problem was is that it didn't really use statistical methods to actually do this. It more talked about like the importance of quality, and quality is great and that sort of thing, but it really didn't have any teeth to it. It really didn't have any statistical measuring methods to actually measure how well you were doing. This led to a lot, the failure of total quality management, I think, actually did lead to a lot of re-engineering of these practices back in the late 80s. And then, in 1987, I think we had the big breakthrough with Six Sigma that was developed primarily at Motorola with an American engineer named Bill Smith. And this Six Sigma has basically taken over the quality control aspect. And so a lot of people, Six Sigma is synonymous with quality control and improvement. So again, Motorola developed this back in the late 80s as a response to the demand for its products. This is a set of management techniques intended to improve business processes by greatly reducing the probability that an error or defect will occur. And again, this goes back to the variability. Six Sigma's primary purpose is to reduce variability. So we want to reduce the variability to the level at which failure or defects are extremely unlikely. That's the goal of Six Sigma. So to understand Six Sigma, you really need to understand the normal distribution plot, which is shown here in our textbook. So here, for example, in a normal distribution, 99.73% of the products are going to fall within plus or minus 3 standard deviations. That's what's known as 3 sigmas. Well, Six Sigma is exactly, you want 99.999998% are going to fall within the lower specification and the upper specification limits. So you can see here as the specification limits get tighter, you produce less and less defective products. So a 3 sigma, you're producing 2,700 parts per million are defective. But at 6 sigma, you're down to 0.0002 parts per million defective. So we're really trying to control the variability of the product. So the book points out a very good example. Let's say it looks like, man, this is pretty tight. Look at even like 3, wouldn't plus or minus 3 sigma be enough? I mean, that's 99.73. But the problem is that, today, if you were just manufacturing one product, and it didn't have any components, that probably would be okay. But the problem is today that all of our parts, like transmissions or even iPhones, consist of hundreds of independent components. All of these components must be non-defective for the product to function satisfactorily. So let's say you have a product that has 100 independent components. Well, each one, if you manufacture each one of them to plus or minus 3 sigma, well, then you would have, 0.9973 for the first component times 0.9973 for the second component. So you would have each component has to get manufactured to the 99.73%. But if you link them all together, basically you have 0.9973 raised to the 100. Because remember, we're talking about a product that has 100 independent components. So you reach down, so if you multiply those out, you come up to 0.7631. So that's the probability that a product is non-defective is basically 76%, which isn't so good, right? I mean, so you start to realize why this plus or minus 6 sigma becomes much more important, because that makes this number a lot bigger. If you plug in the 99.9998 here, you get significantly fewer non-defective items being produced. Another advantage of Six Sigma is that if you have a process that shifts over time. So here's a plot of Six Sigma. So first of all, this plot here is a normal distribution curve, a Gaussian curve, a bell curve. So T is our average of the products characteristic we're trying to measure. So let's say, for example, we're manufacturing a boat, a 3-inch boat. We have a manufacturing process where we're manufacturing hundreds of these a day. T is what our target is. This is where we want the mean to follow. So for example, if we take all those hundreds of boats and we measure them, and we take the average value, we want that average value to be right at T. Now there's going to be some variability. Not every boat's going to come out and be exactly within the specification, the 3-inch specification. Some are going to be a little bit short, some are going to be a little bit long. On average, what they'll do is they'll follow this kind of bell curve. Now, one advantage of Six Sigma is that over time, if our process shifts, for example, and say now, as the machine gets older, maybe the average is shifted down here. But notice we're still within our lower specification limit and our upper specification limit. If the average shifts up a little bit to here, we still fall within our upper and lower specification limits. So Six Sigma gives us much more flexibility when we have natural kind of variations. So, what we may, if you see this kind of thing happening, we can see this on our control charts. We can go in and maybe we need to adjust the machine. Maybe we need a new machine. Maybe the machine's just wore out. Maybe the operator is not paying attention. It's manufacturing the boats. And so all these things we can do using control charts, but using this plus or minus Six Sigma gives us a lot more flexibility. So let's take a look at an example. The book talks about this. He says, let's say a customer orders a typical meal, like a hamburger. Hamburger's got a bun, it's got meat, it's got sauce, it's got cheese, pickle, onion, lettuce, tomatoes, kind of like McDonald's, right? It's got fries and it's got soft drinks. So this meal's got 10 components. So let's say this product is 99% good quality, satisfactory. Well, if you just ordered one meal, it's not bad, right? You got 0.99 raised to the 10th power, comes out to be, 0.9044. So, what's the probability of the single meal is good? It's about 90%. Well, suppose you take your family of 4 out. Well, you take this probability and you multiply by raised to the 4th power again. So now, this is the probability that all the meals are good for each family member. Well, that's about 67%. Well, that's not too good now. Now you're getting down there where it's like, somebody's going to get a bad meal, every now and then, right? So now let's say you go out and eat once a month. Well, what's the probability that all the visits during the year are good? Well, you take this value, raise it to the 12th, you get this value here. So, so that's a very low probability that in a year's time all your meals are going to be good, right? It's less than 1%. So this shows you exactly the power statistics and why it's important to achieve the plus or minus 6 sigma. Because with plus or minus 6 sigma, these numbers look a lot better. I mean, again, you're never going to get 100%, but manufacturing to plus or minus 6 sigma has, with that reduced variability, gives you much better odds of the product being good, especially if it has multiple components to it. A technique that's come along in recent years is what's known as lean, and lean can actually is real basically a set of methods and tools used to eliminate waste. Lean helps to identify anything not absolutely required to deliver a quality product on time. The benefits of lean is that these methods help reduce inventory, lead time, and cost. They also increase productivity, quality, and on-time delivery, capacity, and sales. And you can actually combine lean with Six Sigma. In fact, a lot of people do that, and they talk about what's known as lean Six Sigma. It's just Six Sigma combined with lean to get a multiplicative effect.